Hello, this is Richard Walker from Lucidate. In this series, we've looked at why we build AI. We do it to solve problems that conventional logic-based approaches can't solve. Specifically, we've looked at neural networks to solve classification problems. In addition to the why of AI, we've also looked at the how the networks optimize their weights. They do so by nudging them very slightly in response to lots of training data. The size and direction of the nudge is based on minimizing a cost function. We've shown that calculus, specifically stochastic gradient descent, helps us optimize the weights and biases in our network. Another how is how we build them. We've seen that this is very straightforward using the Python programming language and the Keras API. We haven't yet discussed the what questions. What will be the configuration? By which I mean, what is the ideal number of hidden layers, the number of neurons per layer, our learning rate, our cost function? These are important questions, but they do have vague and fuzzy answers. It depends. It depends on the task you're trying to solve. It depends on how big your inputs and outputs are. It also depends on how much training data you have. Where we've previously leaned heavily on mathematics with its derivations and proofs, we're now going to turn to engineering. A good engineer has a sound understanding of the theory, but an equal understanding that theory will only get you so far. To build effective solutions, one needs to marry that theory to practice and understanding. The reality is there's much room for experimentation. To get the right answer, we're going to use the results of these experiments to derive rules of thumb and best practices. While these heuristics won't necessarily give you the optimum configuration straight away, they will give you a good place to start. We'll see how we can use the tools we developed in the last video to help us tune the network to generate better and better results. Engineering involves trade-offs in design. An under-engineered product will likely break or not work at all. An over-engineered solution will be costly. It may be so elaborate that it introduces failure methods of its own. The really good news here is that the Keras API lends itself to experimentation. It's very easy to build multiple neural networks with different configurations, different numbers of layers, and different neurons per layer. We can then set up a simple competition. We can configure a couple of dozen networks, each with their own distinct topology. We can then hold an Olympic Games of neural networks to see which topology best solves a specific problem. We'll recall that the backpropagation algorithm randomly initializes the weights in each network. Each time we train a network, we will expect a slightly different result. To make our Olympic Games competition more accurate, we'll train each network multiple times. That way, we can look at the max and minimum accuracy, the average accuracy, as well as the standard deviation and the range. These statistics will give us a more thorough way to evaluate each configuration and pick a winner. For a long time, most networks were designed with a trapezoid architecture. That is, each successive hidden layer would have less neurons than the preceding one. The resultant shape of the network resembles a trapezoid. In recent years, it's become more fashionable to recast this shape as a rectangle with the same number of neurons per hidden layer. Let's use examples from both approaches in our Olympic competition. Here we see the various configurations that we will use. We have a variety of networks with different numbers of hidden layers. These networks have a variety of neurons per layer. We also have a mix of trapezoid and rectangle shapes, as well as some hybrids that are fusions of the two. We'll train each network 10 times. Here we plot the results of our competition as a bubble chart. We'll first plot the best results for each network, the maximum accuracy. This max accuracy is plotted on the y-axis. Our x-axis shows the number of trainable weights and biases per network. The size of the bubble indicates the number of hidden layers. The larger the bubble, the more hidden layers. The number of neurons per layer is used to label each point, as is the maximum accuracy achieved. If we look at the chart as a whole, we can see that there's about a 3 percentage points of difference between the worst performing network with 86% and the best at 89%. We see a general positive upward slope. Generally speaking, the more weights and biases a network has, the more accurate it becomes. But we can see some strong exceptions to this rule. Indeed, our best performing network has fewer than 2 million parameters, and it exceeds the performance of networks with more than twice that amount. This is perhaps a very surprising result, but we'll look at some key reasons why this is the case a little later in this video. Stay tuned. Our gold medal winner for this event is a 6-layer trapezoidal shaped network. It has an accuracy of 89.02%. Just behind in silver is a very similar shaped solution with 7 hidden layers. And with 88.84% accuracy, we have a rectangular shaped network with 5 hidden layers of 1024 neurons each. This also turns out to be our largest network as measured by tunable parameters. Firstly, it should be noted that all of these networks work well on this task. Even the worst offers around 86% accuracy, which is remarkable. But I would argue that the 3% pickup in performance between the worst and the best more than justifies the additional experimentation and training time to look at different configurations. Your desired accuracy will be something unique to your use case. Spend plenty of time to determine what an increase of 0.1% accuracy is worth. You'll always be able to tweak a network to get better performance, but there will be diminishing returns. A key component of knowing when to stop experimenting and start productionizing your AI will be based on the specific value that you assign to more accuracy. There are no clear winners in terms of the optimum number of layers, neurons per layer, or shape of network. In many ways, this is encouraging. The accuracy of networks shows some robustness to different configurations. This means that unless the value you assign to a 0.1% increase in accuracy is incredibly high, you don't need to agonize over micro-tuning the architecture of your network. And, as we shall see later in this video, there is a benefit to using clusters of different networks. These ensembles can deliver better accuracy collectively than single networks acting alone. As Aristotle said, the whole is something besides the parts, although I strongly doubt that he was talking about neural networks. And he probably didn't say it in English. At the Olympics, we have different events. Athletes with a physiology suited to kayaking may not be good cyclists. The best gymnasts might not excel at table tennis. Weightlifters may struggle in the dressage events. Might this analogy carry over to neural networks? Let's retrain the same networks on a similar but different task, this time classifying handwritten digits from 0 to 9. We'll keep the contest identical. Each network will have 10 attempts to get the best accuracy score, and we'll record the statistics of each. For this simpler task, our gold medal winner is a 4-layer trapezoid-shaped network. In its hidden layers, it has 1024, 512, 256, and 64 neurons. It achieves a best accuracy of 98.25%. Silver goes to a 5-layer hybrid network, and bronze to a 5-layer rectangular solution. In this simpler task, gold, silver, and bronze all score well over 98% accuracy. In total, 11 architectures get scores over 98%. In this group, we've got a diverse array of solutions: 4, 5, 6, and 7-layer networks, a fairly even mix of trapezoidal, rectangular, and hybrid architectures, and a range of tunable parameters from 743,000 up to 5 million. Indeed, the 743,000 parameter network outperforms its much larger cousin. 10 out of the top 11 best performing network architectures are shared between both tasks, but they're in a very different order. If instead of maximum accuracy, we order by average accuracy and observe the standard deviation, we can see that there's some variation in the accuracy of each architecture per training run. Not a lot, but enough to change our medals table if we choose to rank on average accuracy, like sailing, versus max accuracy, 100 meters, for each configuration. The takeaway here is to train the same architecture several times. Presumably, you'll want to choose the most accurate one once you've done this. It's perhaps unsurprising that architectures with less layers and less neurons have some of the lowest accuracy scores. But why aren't the best solutions the ones with the most layers and the most number of parameters? I'm suggesting here that networks can both be too small and too large. Too small seems intuitive. If there aren't enough layers or neurons per layer, it will be difficult for the network to learn the mapping between the inputs and the desired outputs. When it comes to large networks, our intuition might tell us that a big network might take too long to train, and the extra training time would not be worthwhile for marginal gains. Our intuition would be correct that there's certainly a law of diminishing returns in adding more layers and more neurons. But there is something more sinister lurking that we need to be aware of if our networks get too big. In the literature, this sinner manifestation is often referred to as the curse of dimensionality. Let's discuss what this means and what its implications are. Our networks have a vast number of parameters. When we're training our network, our backpropagation algorithm uses stochastic gradient descent in a huge multi-dimensional vector space. This vector space has as many dimensions as there are tunable weights and biases in our network. As dimensions get large, the distances between points get large. Also, the chances of being near an edge or a boundary case become highly likely. If we have a lot of space between random points, then it stands to reason that we need a lot of training examples to cover a sufficient amount of space for our network to be able to generalize. If we're likely to be near an edge, then we need to make very tiny steps as our stochastic gradient descent moves downhill to make sure that we don't fall off an edge into some multi-dimensional chasm. We aren't talking about spatial dimensions when we talk about high dimensionality here. This isn't a Christopher Nolan movie. What we are talking about is the dimensionality of our vector space when we propagate forward, and specifically when we use our cost function to solve for our nudges to weights and biases during backpropagation. To illustrate this, let's build up our dimensionality gradually. If we just live on a 1D number line, things are pretty easy. If our line is 1 unit long, the maximum distance that two random points can be from each other is 1. The chances of a random point being within 0.01% of an endpoint is 0.02%, and the average distance between two random points on this unit line is 1/3. Nice and cozy. If we scale things to 2 dimensions, things are still very well behaved. The furthest distance 2 points can be from one another increases to 1.41 from Pythagoras' theorem. The chance of a random point being within 0.01% of an edge goes up to 0.04%, and the average distance between two random points can be solved by the box integral. This is quite a complex equation to solve, but it has a simple approximation shown here. The average distance, therefore, will go up to 0.5211. Adding a third dimension means that the furthest that 2 points can be from each other is 1.73 units, and 2 points chosen at random will have an average distance of 0.6616 from each other. Adding a fourth parameter, which is still very low dimensionality for most practical problems, The maximum distance that 2 points can be from each other in a unit hypercube goes up to 2. And 2 random 4-parameter points will be 0.7776 apart. As we add more dimensions, we add more space. The distance between randomly chosen points gets greater. Once the dimensionality gets to 7, the average distance between 2 random points is 1.0515, greater than the 1 unit of each side. If we scale up to 100,000 parameters, then the average distance between 2 random points is over 40 units, and the probability of being within 0.01% of an edge is over 99.9999999%. That was 99 and 7 nines. The reality is there is a lot of space in high dimensions, and most of it is close to a boundary. To bring this back to a practical example, our gold medal winning neural network inhabits a dimension where the average distance between 2 random points in a unit hypercube is 500. For the largest network we trained, this number is 914. So the moral here is adding parameters isn't free. Aside from the small tax of additional training time, every time you add a new parameter, a debt accrues. This debt needs to be paid with additional training examples. Otherwise, the network will be highly susceptible to overfitting. So we've trained a bunch of different networks of different shapes and sizes. They have varying levels of accuracy on our test data. We can gain more accuracy still by taking our best performing networks and making small tweaks to the amount of neurons per layer and retraining. More interesting still, we can use our confusion matrix for each network. When we take a look at this, we'll see that some networks are strong where others are weak. This raises the interesting possibility of combining the results from multiple trained networks to further improve our accuracy. These combinations of AI solutions are called ensembles. If you recall from the last video, we discussed making use of all of the activations from our output layer, not simply the maximum activation. Here we can show the same images to multiple networks simultaneously. We can improve our accuracy by taking an average of all the output activations. Alternatively, we could have each network vote with their max value. Should we wish, we could weight each network's response by its overall accuracy, or use precision and sensitivity metrics to account for the fact that some networks may be better at classifying some inputs than others. In this GUI, the ensemble is on the left, and the constituent components of the ensemble are shown to the right, with decreasing accuracy as one moves right. Here you can see that the ensemble score offers a significant improvement over all the component networks. As in nature, diversity improves the overall outcome. So in this video, we've built and tested several neural networks to solve 2 computer vision problems. We've seen that an engineering approach is necessary to help us find the optimum number of layers and neurons. One shouldn't approach this branch of AI in a one and done fashion. Python modules like Keras and TensorFlow lend themselves to experimenting with a broad range of configurations. Do experiment with a core set of different layers with varying numbers of neurons. From these results, then make finer refinements to find the best solutions. Be cognizant of underfitting by not giving the network enough weights and biases to be able to generalize and solve the problem, but also be aware of the less obvious peril of the curse of dimensionality. This leads to the less intuitive problem of making the network too complicated. This usually manifests itself with overfitting. Finally, there are huge benefits to diversity. Different architectures bring different strengths to the table. These can often overcome shortcomings in individual networks. Building ensembles adds to both robustness and accuracy. This is Richard Walker from Lucidate. Please join me in the next video where we will take a quantum leap forward in the accuracy of our image processing task. We'll introduce convolutional neural networks, or CNNs. These networks perform feature extraction and pattern matching to produce far better results than the networks we have seen so far.